All right, LaChatPrin's principle. We're going to now talk about how we can stress a particular chemical reaction so that we can shift the equilibrium where we want it. Chemistry is nothing if we cannot influence it, right? So this is going to explain exactly how we can influence chemical reactions to give us what it is we want. So here's what LaChatPrin's principle says. If a change is imposed on a system at equilibrium, the position of equilibrium will shift in a direction that tends to reduce that change. Now let me give you an example. This is obviously a waterbed. So let's say that you are going to jump on the waterbed. Here you are. Oh, by the way, this waterbed is at equilibrium. And you are going to jump on said waterbed. So here you are. Whee! And you're smiling because you're jumping on a waterbed. And you jump on said waterbed. So what happens when you land on that waterbed? I think we can all venture to guess what's going to happen, right? Okay, so you're going to fall on the waterbed. You are going to press down on said waterbed. And now the waterbed is going to look like this. And there you are in the middle of the waterbed, without a face this time, okay? All right, so yeah, that waterbed is really bulged up on the opposite side. But if we keep watching that waterbed, if we watch it for another second or so, I wonder what happens. Well, it's going to do this with you on that side. And it's going to keep going back and forth, up and down, up and down. Eventually, though, it's going to come to a new equilibrium, won't it? Okay? Eventually, we're going to get a waterbed that probably looks, if it's a good waterbed, something like this. There you go. Okay, now we have a new equilibrium. So you are the stress on the system. You are imposing a stress on the system. And it doesn't like that. So it's got to relieve itself somehow, so that's why it pushes the water to the other side. Well, water doesn't like all being to that side, so then it rushes back to its original side. Again, the water doesn't love being over there, so it rushes back because you're standing on it. And we get this back and forth odyssey of the mind that eventually results in a new equilibrium. That's chemical equilibrium. Cool stuff, even better artistry. All right. So there are a couple of different ways that we can change the equilibrium. Way number one, let's alter some concentration. Here's the rule. The system is going to shift away from the added component. If a component is removed, the opposite effect occurs. Let us take a look. Here's a particular reaction. We've got A, B, C, and D. We see this reaction a lot. I'm really wondering what C and D are. We're going to investigate a particular change, and then we're going to ask the question, well, how will that change shift the equilibrium? Let's say that we add some product. So we add some C and D. You might say, how can we add product? Well, remember, it's just the way that we define product and reactant. Products on the right, reactants on the left. We can flip any of these reactions. So let's say we add some of C and D. And what will that do? Well, it's going to force the chemical reaction to the left. So an increased concentration of products shifts the equilibrium to the left. All right, let's try something else. Let's remove some products. Let's say we got A and B and they're cooking along and they're producing C and D. We take some C and D out. That's going to have the effect of shifting the equilibrium to the right. Good. And the opposite's also true. If we affect the reactants, if we increase the amount of reactants that we've got, we are going to shift the equilibrium to the right. If we remove the amount of reactants that we've got, we will shift the equilibrium to the left. I think concentration is probably the easiest of the three shifts that you're going to see. All right, so there's concentration. Let us move on. The next one, temperature. So, temperature is weird because with a change in temperature also comes a change in K. So if we change temperature, K is going to change. Not the case for concentrations, because it changes proportionally. Okay? So for temperature, K will change depending upon the temperature. If it's endothermic, the energy is a reactant. Exothermic, the energy is a product. So in my example here, I've got energy as a product. And it's right here. So what's going to happen if I change the temperature of this particular system? If I increase my temperature, so if my temperature goes up, well, what would you think would happen? Think about temperature or energy as essentially being a reactant or product. It's not really, but think about it that way. So if we increase temperature, we're essentially putting more energy in. So we're putting more stuff on the right side. So it's just like the waterbed, right? It's going to try to relieve itself, and it's going to try to come back to equilibrium. So we're going to get a shift to the left. So for an exothermic reaction, an increase in temperature equals shift to reactants. Okay? A decrease in temperature equals a shift to the products. Right? So think about what's going on here. If we increase the temperature, we're going to shift over towards the reactants. We're going to push everything this way. What's the effect in that? Well, if we increase the temperature, then what happens with the FeSCN? Its concentration actually decreases. And the concentration of the SCN goes up. And then the Fe goes up. Well, let's take a look at what K is. For this particular reaction, K is, let me go back here, there we go, FeSCN divided by Fe and SCN. If we decrease this stuff right here, if that goes down, this goes up, and this goes up, what's going to happen to K? K is going to go down, isn't it? K will go down. Yep. So that's why I wanted to make that statement at the beginning of the slide, that a temperature change affects K. Not the case for anything else. Not the case for concentration, not the case for pressure, as we'll see in a little bit. But certainly the case with temperature change. Okay. Let's go to pressure. Now, think of pressure, because we're handling with gases often, all the time when we're talking pressure. So think of pressure as nothing more than adding in more molecules of gas. The system will shift away from the added gaseous component. So most moles of gas. If a component is removed, the opposite effect occurs. So this is very similar to the concentration, is it not? Yeah. Addition of inert gas does not affect the equilibrium position. Wait a minute, we got to review what's inert gas. How about the nobles, right? How about the noble gases? One other one I want to make a big point about. Nitrogen. Nitrogen's pretty darn inert. What does inert mean again? For 8,000 cool points, it doesn't react. It's unreactive. It's very okay being like it is. Okay? So that's inert. They do not affect equilibrium position. All right, let's go to C now. Decreasing the volume increases the pressure. Oh boy, now we're getting crazy. Decreasing the volume increases the pressure, which shifts the equilibrium toward the side with fewer moles of gas. So if we decrease the volume of the container, that is going to increase the pressure. And what that'll do is it'll force the equilibrium towards the side with fewer moles of gas. Why? Because if it has fewer moles, there's less stress. If it has more moles, there's more pressure. Oh my goodness, the stress. Less moles with an increased pressure. Not as much stress. Okay? All right. What about a catalyst? Catalysts are interesting. Well, catalysts don't change K. They don't change K at all. What do they change? Well, they don't shift the position of an equilibrium system from left to right. So what do they change? They allow us to reach equilibrium sooner. So So they don't change K, they have no effect on that. They don't shift the position from left to right, but they allow us to reach the equilibrium sooner. So, as we remember, a catalyst lowers the activation energy for both forward and reverse reactions. It does not change the equilibrium constant or shift equilibrium. Remember I said there were 3 things that we need to be concerned about when shifting equilibrium in LaChatPrin's principle: temperature, pressure, concentration. We do not need to worry about adding a catalyst. It is interesting to know that, it doesn't change K, and it does allow it to reach equilibrium sooner, but we learned that in the kinetic section. Alright, so let's take a look at this stuff in action. This is kind of neat. Let's think about a reactant that we've got here, 2 reactants, hydrogen and nitrogen, again in the Haber process, which is always really, really an important process. If we go ahead and combine these 2 things, we got to combine them in a compressor. We got to compress them, get them really tightly compacted together. High pressures at this point. So what's that going to do? Well, as we force them into what we call a reaction chamber that has a catalyst inside of it that allows this process to speed itself along, the higher pressures are going to want to push the process in the forward direction. Why is that? Well, let's look at the chemical reaction. Remember, if we have high pressure right here, high pressure, there are how many moles? 1 plus 3. There's 4 moles on this side, 2 moles on this side. So the high pressure is going to want to force the reaction to the lower number of moles. And that's what we see. So we get some NH3 to be produced. We still have some residual H2 and N2. That now passes through something called an ammonia condenser. It gets really, really chilly inside of there. It condenses ammonia at its condensation point. We get liquid ammonia, and that gets tossed in the storage tank. Now, even at those really, really temperatures at which we condense the ammonia into the liquid state, hydrogen and nitrogen are like, whatever, it's still hot, it's toasty. So they stay in the gaseous state. So see the separation method? Oh, it's just beautiful. Liquid ammonia, gaseous hydrogen and nitrogen. So the leftover gets pulled out, back up, and reinserted into the process. And it is like the circle of life, back and forth and back and forth. And we waste hardly nothing. Isn't that super? So we can see the mole percent of NH2 and H2 as it rises. We have a decrease. Okay, we have a decrease of NH3. Now, why would this occur? Well, it's because of the temperature scale. We see that as we increase the temperature, we actually force this process in the reverse direction. Okay, we actually produce more N2 and H2. We don't want that, right? We don't want that. We want more NH3. So this process, this particular reaction right here, is going to be run at a really cold temperature in order to favor this direction. Why? It's exothermic. Right? If it's exothermic, let's push it the other way. All right, let's recap. 1, 2, 3, 4, 5 things we talked about. Concentration, pressure, volume, temperature, power. So concentration, will it shift to equilibrium? You betcha. Will it change the equilibrium constant? No dice. Pressure, will it shift to equilibrium? Yep. Will it change the equilibrium constant? No dice. Volume, will it shift to equilibrium? Yep, because it changes pressure. Will it change the equilibrium constant? No cookies. Temperature, will it shift to equilibrium? You betcha. Will it change the equilibrium constant? You could tell from the inflection in my voice that yes, it certainly will. It's the only one that does that. How about a catalyst? Catalyst, you are not welcome at the party. You do not partake in LaChatPrin's principle. This is the catalyst. He's very sad. Okay. So hopefully you get a really brief recap right now of LaChatPrin. I'm telling you, it's all about practice with this guy. You got to practice it over and over and over again. That's what we'll do tomorrow. Okay, have a good night.